Hello everybody, my name is Roxani Hadjipanagiotou. I work at IRES, and in this webinar I will present the lifecycle assessment methodology and its practical application in metal coating development projects. I will first introduce the definition of the lifecycle assessment and present the standards that we use to perform this kind of analysis. I will later explain why is it important to have a lifecycle perspective when we study sustainability of materials. And I will present the framework of the lifecycle assessment according to the two ISOs. Then I will speak a bit more specifically about the NICKEFFECT project. I will use it as a case study to present you how we approach the different steps of an LCA analysis, starting with the goal and scope definition. So here I will discuss the system boundaries, functional unit and reference flow. I will explain to you how we approach the data collection during the lifecycle inventory phase of LCA, as well as how we do the lifecycle impact assessment and interpretation and what kind of results we get out of that. The lifecycle assessment, according to the ISO, the definition is a technique that addresses the environmental aspects and potential environmental impacts of a product throughout its lifecycle, from the acquisition of raw materials through production, use, end of life, and recycling and final disposal phases. There are two ISO standards that we use for lifecycle assessment. These define how the goal scope definition should be performed, describe the process of the lifecycle inventory analysis and the impact assessment phase, the interpretation phase, as well as the requirements for reporting and critically reviewing an LCA report. In addition to the two ISO standards, there is also some open access technical guidance documents from the European Commission, which serve as a common basis for consistent, robust and quality assured lifecycle assessment. And they are also conforming to the two ISO standards, so that is a very useful source of information to get really hands-on experience on LCA. It is important to apply life cycle perspective when we study sustainability for several reasons. It can help with identifying hotspots of environmental impacts, so materials or processes that contribute significantly to the impacts of the product we are analyzing. And it can also help identify opportunities to improve the environmental performance by targeting these hotspots for mitigation, such as replacement of a certain chemical or a certain process with an alternative. The life cycle assessment perspective also helps us prevent problem shifting, both between life cycle stages and impact categories. So what does that mean? Perhaps in the case of the NICKEFFECT project, for example, we select a new metal to replace an existing metal for a certain application, and this new metal might have lower emission impacts during its extraction, which is why we might want to consider using it, but it might have higher impacts during its recycling. So if we don't apply life cycle assessment, then we don't realize that we are just shifting the problem to a different life cycle stage if we don't take the full life cycle into account. Another example of problem shifting could be, again, hypothetically, if we replace one metal with the other, maybe the new metal has lower climate change potential, so that is nice, but maybe it has higher potential in another impact category. So therefore, there, again, we are shifting the problem to a different impact category, and this is something that we can really catch when we perform life cycle assessment, take the full life cycle and all the impact categories of an LCA into account. LCA can also help with decision making in industry or policy level. It can be useful if we want to select relevant indicators in order to monitor the sustainability of a certain product or a product category. And finally, LCA is useful for marketing purposes, for example, for eco-labeling or performing an environmental product declaration on a certain product. The life cycle assessment framework, as presented in the ISO standard, consists of 4 steps. The first step is the definition of the goal and scope. Here we need to describe the reason for executing the life cycle assessment, who is it intended for, what is the product or the service, of course, specifically that we are studying, what is the functional unit of it, to describe its life cycle and its system boundaries. In the second step, the life cycle inventory step, here we need to collect all the resources and all the emissions that can be allocated to the product that we are investigating. So here is the step where we would gather information such as this to produce a certain product, in this case a metal coated electrode, how much electricity we would need to use. So this is where we gather all this information regarding the product we are studying. In the third step, the impact assessment step, here we assess the environmental impacts of the product or service under analysis over different impact categories. That could be, for example, global warming potential or human toxicity potential, etc. Basically, this is the step where we would translate the information we got at the inventory phase, so how much kilowatt hours of electricity we might need to make a certain electrode, into an actual environmental impact. So these 10 kilowatt hours of electricity would imply 3.2 kilograms of carbon dioxide equivalent as climate change potential. Finally, the interpretation step, the final step of the LCA, here we combine the findings of the inventory analysis and the impact assessment. We appraise them and we answer research questions that we posed in the goal and scope definition phase. We draw conclusions regarding the study, and of course we analyze the accuracy, completeness and precision of the data and the methods that we used. I will now go into more specifically the NICKEFFECT project to show how we would approach the goal and scope definition, or how we have approached the goal and scope definition for this specific project. So first of all, to mention the project aim. So here the aim is to develop novel ferromagnetic nickel-based coating materials in order to replace platinum, which is a scarce and costly metal, and to ensure the high efficiency of these new nickel-based coatings for specific applications that typically platinum is used for. There are several objectives to this project. So first, obviously, to synthesize those nickel-based coatings that we are developing, to ensure that the materials being developed are affordable, durable, and have increased corrosion resistance. This is particularly a property of platinum that makes it quite irreplaceable in certain applications. But of course, the objective of the NICKEFFECT project is to develop materials not based on platinum, but based on nickel, which share the corrosion resistance of platinum. Other objectives is to upscale, of course, the material production, so starting from the laboratory scale but reaching to real scale component coating within the time of the project, to ensure that the material development approach that we follow within the project is safe and sustainable by design, to define pathways for the recovery, recyclability, purification and reuse of materials developed within the project, and finally an objective of the NICKEFFECT project to develop a decision support tool which will ensure the adoption of the safe and sustainable criteria in metal coating development. Taking all that into account, we could go on and start developing the goal and scope definition within the NICKEFFECT project as a case study, of course, here in this webinar. So I will start with the goal. As part of the goal, we need to identify the reason for carrying out the study, what are the intended applications of the LCA, and what is the target audience. So in the case of NICKEFFECT, the reason for carrying out the study could be to assess if those novel nickel-based platinum-free materials that we are developing are actually environmentally sustainable. I could identify several intended applications for the LCA study within the context of the project. So that could be to compare the environmental impacts of platinum and nickel-based coatings, to identify hotspots of environmental impacts and identify mitigation actions to decrease those, to guide the development process for nickel-based coatings at different scales, so from the lab scale to the real scale, from a sustainability perspective, so to provide sustainability criteria for selecting certain formulations or protocols to investigate. And finally, to develop sustainability criteria and metrics which can be used in the decision support tool developed within the project. So these are the intended applications of the LCA study we perform in this work. Besides the goal, we also need to define the scope. So the scope should include the assumptions and limitations we have identified for this study, the system boundaries and the value chain of the material we are investigating, and the functional unit and reference flow. In this project, we have identified some possible limitations related to data availability. For example, for the commercial platinum-based electrochemical cells, there is a lot of confidential information that cannot be shared to us regarding how these products are made and what materials exactly are included. To address this, we aim to use literature data to develop the bill of materials for the electrochemical cells, as well as to gather the inventory information for the use phase, the end of life phase of the various components included in the electrochemical cells. There is also limited data availability regarding some input materials produced by upstream providers, so not within our consortium, but outside the consortium, so the upstream providers of our partners, and the materials used in the development of the nickel-based coatings. For some of them, it is not easy to find information on how they are produced. What we can do and what we plan to do to address this is to select literature data to find the best approximation for the upstream processes, and if needed, we can of course always exclude certain upstream processes if we feel like the data quality we get is not the one we want within this LCA study. Then some processes can be excluded and focus only on the materials themselves. Besides the limitation, we have also identified an assumption that we need to make to analyze the systems, this comparative assessment, and that would be that some parts of the electrochemical cell and the balance of plant between the conventional and the novel system are the same, and therefore we can exclude some materials and some processes from the comparative assessment. I will now discuss the system boundaries. Starting from the raw materials, this is a life cycle assessment, so typically we would start from the raw materials used for a certain product. These raw materials are used in a certain upstream processing process, which results in the creation of the input materials, so the chemicals used by the project partners to develop the nickel-based coatings. Then the partners within the project perform the synthesis of the coatings, resulting in the formation of the final coating. This undergoes a certain manufacturing process in order to create the demonstrator. Of course, the demonstrator is used for a certain amount of time for a certain function until potentially it becomes defective or reaches the end of its life cycle in any case. Where different waste treatment processes can take place, and in addition to that, also it is possible to either refurbish the defective devices so that they can be returned to the value chain and reused, or there could be a recycling process which might result in the recovery of a certain element, nickel most likely in this case, which can be therefore reused in the synthesis process of the nickel-based coatings. There is also, of course, transportation taking place between different process steps along the value chain, and there is also packaging material involved along the value chain in certain process steps, which need to be taken into account within an LCA study. And I will discuss a bit more the system boundaries. So the one I show here, starting from the raw materials until the formation of the nickel-based coatings of the product, that would be a cradle-to-gate approach to LCA. The purpose of an approach like this would be, for example, to compare different input materials or alterations to a certain manufacturing process which do not affect the final product. So then it makes sense to focus on the raw materials and to focus on the synthesis process, because there is where we are changing the protocol, but eventually the nickel-based coating that results from this synthesis is the same, whether we follow approach A or B, so therefore we do not need to take into account the rest of the life cycle and we can focus only on the cradle-to-gate part. Another type of system boundary that we can encounter in an LCA study is what we refer to as the gate-to-gate. So here we do not start from the raw materials, start in this specific example from the input materials, and we reach a certain product, a certain gate of production, but we don't go all the way until the end of the life cycle. Why would we use such system boundaries? For example, we could use them to compare alterations in the manufacturing process that do not affect the final product. If we were in the synthesis step, if we wanted to use different metal deposition methods, but we knew that this does not affect the performance of the final product, then we could apply system boundaries like this shown here. Finally, what we typically most commonly would say encounter in LCA is what we refer to as the cradle-to-grave system boundaries, so taking into account the full life cycle of the product under assessment. So to make this a bit more clear to everyone, I will show a more specific example of how these system boundaries would work within the NICKEFFECT project. In the case of raw materials, of course, given the nature of the project, in my example, I will start with nickel ore. In order to use ores of nickel metal, we need to, well, mine them, obviously. The mining process itself requires some equipment and some fuel. And it produces, besides the product, the nickel ore, also emissions and solid and liquid waste that need to be treated somehow. The treatment process itself of the waste generated along the life cycle also has, if you think about it, a full life cycle behind it. So how the treatment process takes place and what chemicals we might need or what kind of equipment we might need to treat a certain type of waste, that is a whole full life cycle of materials that need to be taken into account. And actually the same goes for every input and output within an LCA. So in order to produce the equipment that we use during the mining, we need to think about metals or other types of inputs that need to be used to create every piece of equipment we might use along the life cycle of a certain product. The same goes for the transportation and the packaging materials, of course. And for every process step that we saw in this life cycle, so for example, for the upstream processing of nickel ore in order to create the nickel salt, the resource that we use for the deposition of nickel coatings, there is resources needed to be inputted in the system, and there is products, waste, and emissions generated from the system boundaries and escaping to the ecosphere. For the synthesis process itself, so the protocols developed within our consortium for the development of nickel-based coatings, we also need a lot of inputs and outputs. We need energy, protective equipment potentially, consumables, other equipment, auxiliary materials or resources. So besides the raw materials themselves, the nickel salt, we also need all these kinds of other inputs in order to produce the nickel-based coatings. Of course, there is also waste and emissions during the synthesis process, so maybe some solvent evaporates or some liquid waste or solid waste is generated, and also all the other equipment we mentioned, such as the consumables and the protective equipment, also constitute a waste generated by the synthesis process that needs to be taken into account in an LCA study. And of course, all these inputs and outputs of every process step along the life cycle of the nickel-based coatings also has, let's not forget, a full life cycle behind it for producing the materials and the equipment needed. So all this input is required to make the final product. In the case of the NICKEFFECT project, that is a nickel-coated electrode. The nickel-coated electrode itself undergoes a manufacturing process and is incorporated in a demonstrator. In this case, that would be an electrochemical reactor. Then we need to take into account, of course, the use phase of the demonstrator. That would imply that there is inputs that we need to consider, reactants, reaction medium, energy, other materials needed to run the reaction, etc. And there is, of course, also outputs. So the product itself, of course, the thing that we designed the catalyst to create, but also there is potentially side products, spent medium, equipment and resources needed for product separation and purification, etc. So to take into account the full life cycle of the nickel coated electrode that we are investigating in this particular case study, we need to take into account all these steps. Eventually, the nickel coated electrode is not functioning as we want it as a catalyst anymore, so then it reaches the end of its life cycle. In the case of the NICKEFFECT project, that probably means some sort of recycling process to recover part of the metal, and potentially for other materials we need to consider processes like waste incineration or landfilling to deal with the waste at the end of the life cycle. I will now discuss a bit more about the foreground and the background system of an LCA study. So the background system includes all the processes within the system boundaries that can be performed by many suppliers and clients. So they don't need to be specific to a certain supplier or client. We can use homogeneous market average data or generic data from internet resources to simulate those processes. It also includes processes that are not under the direct control or the decisive influence of the producer or operator of the process, of course, or product we are investigating. So, for example, that could be the upstream process of producing the chemicals, the nickel salt we saw earlier, or the process to produce the generic electricity mix of a certain country that our facilities are based in. So based on this, actually within the NICKEFFECT project, you would expect that our foreground system starts from the synthesis until the demonstrators and everything else belongs to the background system. There are exceptions to this. So for example, if a certain product has specific characteristics that affect the use phase or the end of life phase, then we need to take them into account by combining foreground information with generic data. In the case of the NICKEFFECT project, an example of that could be if we were investigating different scenarios for the source of the nickel from recycling processes, for example, of other formulations of nickel, then that means that in this case we would have to include in the foreground system and take accurate data both for the recycling process as well as the upstream processing of producing the nickel source. Another exception is to this rule about what belongs to the background system is whether there are specific scenarios that relate to the use phase and the end of life phase. Then these phases need to be considered within the foreground system and get specific data. So for example, if our demonstrators were specifically designed for easy disassembly compared to a market average product in this project, then actually the end of life phase and the refurbishment phase would have to be included in the foreground system, which means that we would have to contact partners within the project to get detailed, accurate data, and we could not just simulate the information with something from an LCA library or literature. So I described what is the background system. So what is now the foreground system? Well, everything that is left, essentially. So here we are dealing with processes that are specific to the system. So it requires high quality information, accurate data that are specific to the process that we are studying. Typically, that involves all the processes that take place at the commissioner's facility. So the person who hired us to do the LCA is usually the one that is performing these processes belonging to the foreground system. It could also be downstream and upstream processes, so outside the facilities of the commissioner, but processes that cannot be replaced by market average data. So if we have only very few suppliers of a certain material or only very few customers that are interested to buy the material we are producing, then those suppliers or customers need to be included in the foreground system. We need to get high quality information for the processes at their facilities along the life cycle. An example of that would be if we were using certified green energy or certified resources from a specific source somewhere along our value chain, then we would have to get accurate information of how these resources are exactly produced at this specific source. The foreground system also involves processes that are directly affected by the decisions analyzed in our LCA study. Involve processes that are under direct control of the commissioner, or for example, in the case of made-to-order products and services, where the buyer has direct control of the processes, then these also need to be included in the foreground system. In the case of the NICKEFFECT project, based on what I described earlier about the objectives and the outcomes of the project, this is actually a foreground system. So starting from the synthesis process all the way until the use phase, but also taking the recycling process into account, since there is a specific task regarding the recovery of nickel-based sources within the project. I will now discuss the functional unit and the reference flow as part of the goal and scope definition within the case study we are discussing based on the NICKEFFECT project. The functional unit needs to be a precise quantitative description of the function provided by the analyzed system, by the analyzed product, and it needs to specify the qualitative and quantitative aspects of the function along the following questions. What function, how much function, how well is the function performed, and for how long? In the NICKEFFECT project, an example of the functional unit could be 100 kilograms of dry hydrogen after 2,000 hours of operation of the electrochemical system with the nickel-based catalyst at a specific cell voltage and temperature. So let's look a bit at this definition. We have answered the question what, so the function that we want our product, our catalyst to make is to produce hydrogen. We have defined how much, we want 100 kilograms of hydrogen. We have defined how well, we haven't, because that is very specific to the demonstrator that is being developed, but we of course expect our project partners to define us a specific cell voltage and temperature for optimal operation of this catalyst. And finally, we have defined for how long. So we want the specific duration of operation of this catalyst to produce this amount of hydrogen. So we have defined the functional unit. What is now the reference flow? The reference flow is the amount of product required to deliver the desired performance defined in the functional unit. So basically, how much catalyst we need to produce 100 kilograms of dry hydrogen after 2,000 hours, etc. The reference flow is basically the flow to which all other input and output flows, so all the input materials, electricity, waste, etc., need to be reported to us. Examples of a reference flow. So let's assume that the nickel-based catalyst that we are developing has the same functionality as the platinum-based catalyst. So that means that the reference flow in this case would be the same amount of catalytic active area in the same size of electrochemical cell operating for the same duration. Now, if we assume that our nickel-based catalyst has lower selectivity compared to the platinum one, then basically the comparison would look a bit like this. So we would need to compare more of the nickel catalyst compared to the platinum catalyst in order to get to the same function and therefore do the assessment on an equal functionality basis. Finally, if our nickel catalyst had lower stability, for example, compared to the conventional platinum one, then we might want to consider that the electrochemical cell would run for a certain amount of time, and then we would need to replace the catalyst as it has deactivated and run it for a bit longer with a new layer of nickel-based catalyst to get to the same activity as the platinum-based system. So the reference flow basically aims to equalize the two systems being compared, the platinum-based and the nickel-based, based on their function. I will now continue to the inventory data collection phase. This is typically performed via questionnaires in an Excel form, which are sent by the person performing the LCA to the person commissioning the study, so potentially the producer of a certain material that needs to be assessed, as well as other corresponding partners or providers or upstream or downstream partners in any case. It is always possible to plan some bilateral meetings with different partners or even visit the facilities if needed to collect accurate information about the process and the materials under assessment. We should keep in mind that the data collection is an iterative process, so it starts at the start of the project and it continues throughout the project. And typically there will be multiple versions of the questionnaire developed throughout the project. And I should already warn you that the life cycle inventory phase is the most demanding task of an LCA assessment. Let's say, for example, that we are analyzing the development of nickel-based coatings within the NICKEFFECT project. So obviously, to no one's surprise, a nickel precursor is needed to be used in this protocol. So what kind of information would we need from the partner doing this synthesis protocol? We would have to know how much of this nickel-based precursor is used per amount of product produced. We would like to have some information about the product itself specifically that is being used. So for example, what is the product code or where is it bought from? When we have this information, then we can do some research by ourselves to figure out, for example, where the product is produced. So then we can take into account properly the impacts of transportation of this input material to the final product being assessed, which is the nickel coating. If we are lucky, based on the information of the provider, we might find an environmental product declaration already for this input material. That is a very fortunate scenario, because an environmental product declaration is basically a completed LCA study. So as you can see in this table, we have all kinds of impact categories typically encountered in an LCA assessment in the different rows, and in the different columns we can see that for each stage of the life cycle of this input material, in this case the nickel precursor, we can know the environmental impacts for each stage separately if we have the environmental product declaration. It is a document that also is reviewed very carefully before it is published, and it has a certain duration, so it expires after a certain amount of years. So it also we can expect that the type of information and inventory and results in an environmental product declaration are up to date. Of course, this is not very likely that you will encounter EPDs for all your chemicals when you do an LCA, so there is obviously other ways to find information. You can go to your LCA software, which probably has an LCA library loaded in it. Or if you cannot find the information that you're looking for there, you can also consider using other sources of LCA data, LCA libraries. OpenLCA, for example, is quite a good source of also some open access data, but also quite a variety of different libraries. And if you cannot find a process in an LCA library that correctly shows the impacts of the product that you're interested in, it is always possible to try to find, for example, literature that has performed an LCA previously on this specific product. So then maybe you can use the inventory developed in a certain paper to approximate the production of this product. Another approach would be to try to see what is the chemical structure of the product that you are trying to analyze, the nickel precursor in this case, and see if you can simulate the production of this chemical based on information that you find online. Always useful to look for a safety data sheet when you're analyzing chemicals in an LCA. We can get all kinds of useful information from this type of document. So, for example, very important, the composition. And okay, I have to admit this was not a very good example to choose in this case. Of course, needed as the project is about nickel, but the nickel oxide I used as an example so far has, well, quite a basic composition. It is almost pure nickel oxide. So if I may, I will adapt my example. Let's say, for example, that we are creating an electrode that uses silver paste somewhere during its development. That is a much more interesting product to look the MSDS and look at the composition, because as you can see, it consists of a lot of different chemicals, and also because it is a proprietary product, we cannot have the exact composition, that is not revealed, so we have to work with ranges of percentages of different components. So what do we do in this case? Well, you could consider running the LCA twice, taking the minimum and the maximum concentration into account, and yeah, just see how different the results are. But of course, if you have a complicated system with a lot of these chemicals, that can be too many combinations. So what I would typically do in this situation would be to use the average value within the range of concentrations we are given here, and then at the end perform a sensitivity analysis to see if my assumption had a significant effect on the results. So here we can see how I have modeled this silver paste product based on the information we saw in the previous table in my LCA software. So for 1 gram of silver paste output, I have different inputs from the technosphere down here, all the components that we saw in the previous table, with the amount corresponding to the average concentration reported in the table. Let's look a bit more detailed at what exactly I have selected from the LCA library. So for the silver, which of course is part of the silver paste we are studying, as you can see, I have selected a global process. This is because I don't know, as an LCA practitioner, where the silver came from. I don't have a direct communication with the provider of the silver paste. They are not part of the project, so it is not very easy usually to get information from people not involved in an LCA. So therefore, I choose a global process to just get a bit of an average situation on global silver production. Also, of course, I have no access to information related to transportation or packaging, so typically you would use a market library process in this case. So these would include some average impacts of transportation, packages, losses during the transportation, so gives you a bit of a more accurate situation of the upstream value chain without you needing to know exactly what the impacts are. And you might wonder what is actually included in this market global silver production process. So if I go into details into the process in the LCA software, I see that this process includes the mining of silver and the refinery of the ore at 6 different geographic areas. It also includes recovery of silver from different waste streams, so not all the silver involved in this library process is virgin. Some of it is recovered from waste. Also, part of the silver included in this library process is recovered as a byproduct from the production and processing of other metal ores, so as a co-product or a byproduct of another process. Obviously, some of the silver is primary, so some primary metal production from concentrated purification processing is included in this library process. And as I said, it is a market process, so actually transportation is also included via sea and via road. Another thing I would like to draw your attention to now is regarding these two chemicals that we see here. And that is because if you were really paying attention earlier, you might notice, of course not, it's quite a detail, but these two chemicals I have selected in my LCA software here are not the ones that I found in the MSDS. So they are proxies that I selected because I couldn't find the exact chemicals I needed in my LCA library. And this is something that you typically encounter in an LCA. It's very unlikely that everything you need to model will be included in the library. You might, for some of the inputs, need to select suitable proxies. So how do you do that? In this case, I looked at the chemical structure of the two molecules I needed to find a proxy from. I made the assumption that if the chemical structure is similar, then that means that probably the upstream production process for these chemicals is similar. So let's look at the first one, where I used isopropyl acetate as a proxy for the second compound. The chemical structure is relatively close, at least it is the closest one I could find in the LCA library. And my hypothesis was not that far off. Both of these materials are produced by an esterification reaction, which includes an alcohol with acetic acid in the presence of an acid catalyst. So actually, indeed, the upstream production process is pretty close between the chemical I needed and the chemical I found as a proxy. The other set of chemicals, so the original one and the one I replaced it with, somewhat also similar chemical structure, somewhat also similar upstream production process, not exactly as a close fit as the previous example, but both of them are a reaction between an alcohol with a certain compound. And if we actually look a bit more upstream, even though the phthalic anhydride and the terephthalic acid are not the same compound, both have the same resource upstream, so both are produced from xylene. So again, not ideal, but not that far off in terms of proxies to simulate the upstream production process. Of course, after the assessment, it is important, if you have selected proxies, to quantify what is actually the impact of the proxy to the overall product. And if it is very high, that means that maybe you need to find a more accurate proxy, just to have more specific results for the chemical you need. Of course, it is also possible that you cannot find a suitable proxy based on chemical structure. So then what you could do is to model the production of the chemical you're missing based on its stoichiometry. So in this case, for this compound, I can see what reaction is used to produce it. And therefore, in order to model those 390 grams of product output, I will simulate that as the sum of the inputs of chemicals needed for its production, so the 166 grams of acid and the 260 grams of alcohol for its production. There are obviously disadvantages if you go for the stoichiometry-based approach, because at least when we chose a chemical proxy, then things like the catalyst needed or the solvents needed, the purification and the energy needed for the reaction were taken into account. It was not the same reaction, of course, but at least they were included in a certain to a certain extent. And if you go for the stoichiometry-based reaction, then you simply just don't include those inputs. So you are underestimating the impact of your chemicals. And which approach is better? Actually, I don't have a response to that. Ideally, you have enough time to do both and compare the results and see how far off you are with one or the other method. Going back to the original scheme, because we took a bit of a detour, other information that you can find in an MSDS of a certain chemical has to do with the hazard identification section. So here, for example, we see things like needed a well-ventilated area, we need face protection, eye protection, so that kind of gives me a clue that I should ask the partner that is responsible for developing these hypothetical electrodes, what kind of protective equipment they use, or what kind of fume hoods or other ventilation systems they use, because these might have a significant impact on the energy product consumption of the process or the material used. Other information that we can get from this section has to do, for example, as I said, with ventilation or cooling. So I might need to ask whether there is a fridge needed to store the material for a certain amount of time. And another interesting section of an MSDS has to do with the stability and reactivity. So here, for example, I can get potential information about possible emissions of this chemical if it is heated at some point during the production of the electrodes. Not to mention that I can also look up the individual components of the silver paste that we saw before and try to determine whether something might evaporate among the individual components, which I might need to include as an emission in my LCA study. Going back to this original scheme, other information you need to ask the partners responsible for a certain protocol is related to the packaging and the waste treatment of the packaging material. So here, for all the chemicals used in a certain process, I would have to know what is the type of packaging, what is the weight of packaging, so the amount of empty packaging weight per amount of product. What do they do with the empty packaging waste that is generated during their processes at their facilities? And actually that brings an interesting point. Do people actually know what happens to the waste after they leave the production facilities? Often when you do an LCA, you will be talking to someone working in the lab who has just a certain bin that they know they need to throw a certain type of waste, but they might not know what happens to it after it leaves the facilities. And of course, that makes sense. That is not their job. It might be something that technical staff at the facilities knows. So it's always useful, to ask some laboratory technicians, for example, what happens with the waste generated in the lab. Of course, based on the type of material, you can always look into your LCA library and find a process for the treatment of this type of waste. You can research online what might be common waste treatment methods for this specific type of waste and for the specific country, by the way, that you are working with, because that also makes a difference. And obviously, you are always allowed to combine library entries, especially if you have a mixture of different types of waste that you want to properly simulate. You might want to add some different waste treatment options based on the composition. So in this example, we are talking about the glass vial where the silver paste is stored in. And it makes sense that some of the paste will actually be stuck on the glass when the bottle is empty, that cannot be reused anymore. So I was curious what percentage of paint might actually remain in the glass, and how do I model that as an emission to the environment during landfilling or incineration or whatever treatment process they do with the glass. And based on these results that I found using AI, 5 to 10% of the total amount of silver paste might get stuck on the glass. So then I decided to model my waste treatment process like this. So we have the 50 grams of the glass itself, but also a certain weight of, well, in this case I used as a proxy a hazardous spent solvent mixture to simulate the silver paste. So in the protocol of creating those hypothetical, again, silver-based electrodes, of course, besides the silver itself, there is other inputs. So we need the electrode substrate itself and a bunch of other stuff needed to produce these electrodes, such as consumables, crucibles, solvents, binders, cleaning supplies, equipment maintenance supplies, etc. From the process, besides the product, obviously, there is also emissions, solid and liquid waste generated that we need to take into account in our LCA. And there is other steps along the life cycle that we need to collect all this kind of detailed data for. So there is the electrocatalytic reaction taking place after we produce the catalyst that also has inputs and outputs that we need to study. And there is an end-of-life phase also with inputs and outputs that we need to take into account into our inventory. What is important for data collection is that you ask the partners completing the questionnaire to, as much as possible, allow the quantification of all the inputs and outputs per amount of product. So, for example, for this silver paint, we have allocated the amount of glass material to a certain amount of silver paste contained in the glass, and we have also correlated it to how much silver paste we need per electrode. So then we can fully quantify and allocate the impacts of the glass packaging to 1 or 10 or 100 electrodes. For some things, it might not be possible to directly quantify it compared to the product. It might be more of a unit of time kind of a relationship, but then still, please consider asking your partners to provide some information to try to relate this. So, for example, you might have something in the lab that you replace once every certain amount of time, but then you also need to ask the partner to indicate how many products do you make in that duration of time, so you can do the allocation of the impacts accordingly. Finally, I didn't mention it before, but of course electricity use is a very important part of the LCA, typically, especially at the laboratory scale. As we are now examining the NICKEFFECT project, it has quite a significant impact. Ideally, you can measure the electricity consumption in the lab. Of course, that is not always possible, so alternative ways to model the electricity use is to use literature that may have described similar processes before and has reported the electricity use, other online sources, or even just multiplying the wattage of a certain device by the duration of use of the device to get the maximum energy consumption that it can have. So, we are now reaching the life cycle impact assessment stage of the LCA after we completed our inventory analysis. So in this stage, we will categorize and quantify the potential environmental impacts of the materials, processes, emissions in the inventory. We will use an impact assessment methodology which has several impact categories over which it quantifies the impacts, so that can be climate change, ecotoxicity, resource depletion, etc. The impact assessment methodology used in an LCA and the impact categories it contains are already defined in the goal and scope of the study. So, for example, for the upstream production of the silver that we saw contained in the silver paste, per 1 kilogram of silver, during the impact assessment phase, we can get insights such as how much climate change potential it has. So in this case, for this silver product, that would be almost 460 kilograms of carbon dioxide equivalents per kilogram of silver. That's quite a high climate change potential. During the impact assessment, we can identify hotspots of the impacts. In this case, for these kilograms of CO2 equivalent, the majority of them are due to the process of mining and refinery of primary silver. And we can even see exactly which emissions and which chemicals cause this impact. So in this case, for the climate change potential of this silver material, the majority of the impacts is due to actual CO2 emitted to the atmosphere, where about 9% of the impact is because of methane emitted to the atmosphere. In LCA, we refer to these specific chemical emissions that I'm showing here as elementary flows. Elementary flows are exchanges of elements, molecules, or resources between the ecosphere, so the environment, and the technosphere, so the artificial system within the system boundaries of our LCA study. The environmental impacts in life cycle assessment are due to those elementary flows, and different flows, different chemicals have different contribution to the impacts. So for example, specifically for the climate change potential that we are discussing here in this specific impact assessment method that I'm showing you, 1 kilogram of carbon dioxide emitted to the environment corresponds to 1 kilogram of carbon dioxide equivalents. That makes sense. But 1 kilogram of methane emitted corresponds to 37 kilograms of CO2 equivalents. So basically, specifically in the case of climate change, this is because of the radiative forcing potential. So how much a molecule or a compound or an element contributes to the specific impact category that we are examining. That determines the different characterization factors that elementary flows can have. Besides the climate change potential, we can look, of course, at other impact categories as well. So for this 1 kilogram of silver that we are discussing, I can also show you what the resource depletion potential is. So with the same logic that for climate change, we express things as equivalents of carbon dioxide, for resource depletion, we can also express all the elementary flows and the impacts as an equivalent, in this case specifically, of antimony taken from the environment. If we look into more detail, if we want to identify hotspots within the resource depletion potential of silver production, the majority of the impact, so 95%, is due to the mining and refinery of silver. More specifically, if we want to look at the elementary flows that are responsible for these impacts, then we see that 52% of them are due to gold depletion from the environment and 44% are due to silver depletion. So this actually brings up a good question, and that is, why do we encounter gold as an element being depleted during the production of silver? The reason why this is happening is because silver is often a byproduct of the mining of other metals, such as gold. And typically in LCA, when we have a process that produces multiple outputs, then we divide the impacts of the process over the different outputs using a certain allocation method. So the elementary flows, in this case the resource depletion of the entire process of extracting gold, silver, and whatever other metal is included, is allocated to all the different product outputs, and that can be based either on the physical allocation method, so higher the mass of a certain product output, the higher the share of impacts it carries, or economic allocation, so the higher the price, the value of a certain output, the higher the share of impacts it carries. So basically this, the fact that we sum up all the elementary flows and divide them over the different products, is why we can encounter gold as quite a significant contributor to resource depletion during silver production. Besides climate change and resource depletion, we can also look at other impact categories. In this case, I will show you the ecotoxicity potential impact of silver production. And we can again see which processes and which elementary flows contribute significantly to that. So the highest contribution is due to the mining and refinery of the silver. And zinc production from concentrate also has quite a significant contribution to the ecotoxicity potential. I remind you that this silver production process that we have used from the LCA library includes also some silver produced as a byproduct from the processing of other metals. So this is why zinc appears to be a contributor in this process. And aside from the hotspots in terms of process steps, we can also identify specific substances that explain this impact. So the highest percentage of freshwater ecotoxicity potential for silver production comes from the emission of hydrogen sulfide to water during its upstream production, and other impacts are due to aluminium emissions or chlorine emissions, again during its upstream production. And I think it is an interesting comparison to make at this stage between silver and another metal with quite known high toxicity, that is lead. So in terms of freshwater ecotoxicity potential, when I compare 1 kilogram of silver with 1 kilogram of lead, what is interesting to notice is that silver has a much higher freshwater ecotoxicity potential. So we are looking at 3.6 times 10 to the power of 4 versus 4.5 times 10 to the power of 2 for lead. We can also, of course, see which processes and which inputs, elementary flows are responsible for this impact. So the majority of impacts for lead production are due to the mining of lead concentrate. And we can also see, as I said, which compounds are responsible for this ecotoxicity. So again, highest contribution due to hydrogen sulfide emissions to water, and actually a lot of other elementary flows responsible for the rest of the impact. It is interesting to note that lead itself, with again quite known high ecotoxicity potential, has a very minor contribution to the impacts of freshwater ecotoxicity. And it's always important to keep in mind that these results that we are looking at here, so the actual potential ecotoxicity score for each metal and the contribution of different elementary flows, all highly depend on the impact assessment method selected. So for example, what we are seeing in this graph is the comparative impact of lead compared to silver with two different impact assessment methods. So with the blue color, we see the environmental footprint method, and with orange, we see the impact world class method. So when it comes to human toxicity, lead compared to silver has around 12% of the impact. So if silver has 100% impact, that lead, the impacts of lead correspond to around 10 to 15% of that with the environmental footprint method, whereas with the other method, with the impact world class method, the impacts of lead over silver are much lower. We are talking less than 5%. And if we look at the mineral resource depletion impact category, so the second bars we see in this graph, actually we see here the opposite. So the impacts of lead over silver for mineral resource depletion with the impact world class method are around 5%, whereas with environmental footprint method, they are so low that we can actually not see them in the graph, much less than 1%. So yes, this is to demonstrate that the impact assessment method used has quite a significant effect on the results. And again, we should point out here that the elementary flows, so the amount of hydrogen sulfide or lead or silver or whatever other metal that is released to the environment, those are the same. What is different is the characterization factors that each of these two methods use that result in this difference in the impacts. So as I said, LCA allows hotspot identification. We can do that, of course, within each of the chemicals, but we can also do it for the full formulation. So for example, here we can see that per 1 kilogram of silver paste itself, so the entire formulation, in terms of climate change, the majority of the impact is due to the silver, whereas in terms of freshwater ecotoxicity, we see that other compounds such as the isopropyl acetate or the butyl acetate included in the formulation also have a measurable contribution to the impacts. Life cycle assessment also allows us to compare between alternatives of different materials. So, for example, here I show you the impacts of 3 different possible metals that one could use for the development of electrocatalysts, and what are their comparative impacts over 3 impact categories. So we can see that in terms of climate change, tantalum oxide has the highest impact. The same score we see for the freshwater ecotoxicity potential, whereas for the resource use impact category, we see that the antimony has the highest impact compared to the 3 metals we are comparing. Finally, and this will be my closing slide, I will very briefly discuss the interpretation step of a life cycle assessment. So here in this stage we would perform data analysis, of course, on all the results we have gotten. We would use these findings from the impact assessment to answer research questions that we set in the goal and scope stage. We would visualize the data and of course, very importantly, evaluate both the inventory we have developed and the impact assessment, the results we have achieved, over different metrics. So we would have to look at the data quality, completeness, precision, methodological appropriateness, sensitivity, consistency, and representativeness. And both the ISO documents and the other technical guidance documents I mentioned earlier, the ILCD reports, offer very valuable information on how to do this evaluation of the achieved results. And with that, I would like to close this webinar. Thank you everyone for your attention, and of course, me and my colleagues from IRES are always available to answer any questions that you may have about what we discussed today. Thank you very much.